What if I told you that the empty space around us isn't really empty at all, that even in the deepest voids of the cosmos, there's a hidden energy, a restless, invisible force shaping the fate of the universe itself? This isn't science fiction, it's one of the greatest mysteries of modern physics, a puzzle that connects two of the most enigmatic phenomena we've ever discovered: dark energy and quantum vacuum fluctuations. And the deeper we look, the more astonishing the connections become. Picture this: the universe isn't just expanding, it's accelerating, flying apart faster and faster, as if some unseen hand is pushing galaxies away from each other. Scientists call this dark energy, a mysterious force making up nearly 70% of the cosmos. But here's where it gets even stranger. At the quantum level, empty space isn't calm or still. It's a seething sea of virtual particles popping in and out of existence, a phenomenon known as quantum vacuum fluctuations. These fleeting bursts of energy might hold the key to understanding dark energy's grip on the universe. But how and why do these two seemingly unrelated concepts keep crossing paths in ways that defy our expectations? That's the journey we're embarking on today. We'll explore 32 unexpected connections between dark energy and quantum vacuum fluctuations, each one a piece of a cosmic puzzle that could rewrite the rules of physics. From the mind-bending behavior of empty space to the startling ways these forces might be entangled across the fabric of reality, we're diving into the frontier of human knowledge. By the time we're done, you won't just see the universe differently, you'll feel it, because this isn't just about equations or distant stars, it's about uncovering the hidden rhythms of existence itself. So let's begin. To grasp the sheer strangeness of dark energy, think of the universe as a runaway train, only instead of slowing down, it's inexplicably speeding up. Scientists first stumbled onto this cosmic shocker in the late 1990s, when observations of distant supernovae revealed something impossible. The expansion of the universe wasn't just continuing, it was accelerating. This wasn't just a tweak to the rules, it was a revolution. Suddenly, we had to confront the idea that empty space itself might be imbued with a repulsive force, something we now call dark energy. But here's the twist: the more space expands, the more dark energy seems to appear, creating a feedback loop that could one day tear galaxies apart. Now, let's zoom in way in to the quantum realm. Even in what we call a vacuum, space is anything but empty. It's a turbulent ocean of particles flickering in and out of existence, so fleeting they're dubbed virtual. These quantum vacuum fluctuations aren't just theoretical quirks, they've been measured in labs, proving that so-called nothingness is alive with energy. And here's where things get mind-bending. Some physicists believe these tiny, chaotic bursts might be the hidden source of dark energy's push. Imagine billions upon billions of these microscopic pulses adding up across the vastness of space, their collective effect warping the universe on the grandest scales. The connection gets even wilder when you consider the numbers. When scientists try to calculate how much energy these quantum fluctuations should contribute to the cosmos, the result is off by a factor of 10 to the power of 120. That's a 1 followed by 120 zeros, the biggest discrepancy in science. It's as if we've found a single drop of water, and somehow the math says it should be an ocean. This cosmological constant problem hints that we're missing something profound, a bridge between quantum mechanics and gravity that could rewrite physics. Could dark energy be that missing link, or is it something even stranger, a shadow of deeper laws we've yet to uncover? One compelling clue comes from the way dark energy behaves. Unlike matter or radiation, its density doesn't dilute as the universe expands. Instead, it stays constant, as if space itself is generating more of it. This eerily mirrors how quantum fluctuations operate, a ceaseless roiling that doesn't fade with time. some theories suggest dark energy might be the leftover energy from these fluctuations, a kind of cosmic background hum we're only beginning to hear. Others propose even more radical ideas, like hidden dimensions or new fields permeating reality. What's clear is that solving this puzzle won't just explain dark energy, it could unveil a whole new layer of the universe's design. So where does that leave us, staring into a cosmic hall of mirrors, where the very small and the unimaginably large reflect each other in ways we're just starting to trace? Every new discovery peels back another layer, revealing how deeply entangled these phenomena might be, and as we piece together the clues, one thing becomes certain: the universe is far stranger, far more interconnected than we ever dared to dream. If you could shrink down to a scale smaller than an atom, you'd witness a spectacle far wilder than anything in science fiction. Empty space isn't a silent void, it's a churning, frothing ocean of energy, where particles flicker into existence and vanish in the blink of an eye. Physicists call this quantum foam, and it's the closest thing reality has to pure chaos. These aren't just theoretical oddities, virtual particles, ghostly twins of matter and antimatter, constantly erupt from nothingness, borrowing energy from the universe before annihilating each other in a dance that defies common sense. But here's where it gets cosmic. While each quantum fluctuation is unimaginably tiny and fleeting, their combined effect might be shaping the fate of the entire universe. Think of it like raindrops on a pond. A single drop creates a ripple too small to notice, but trillions of drops together can shift the water's surface in ways that alter the pond itself. Similarly, the ceaseless bubbling of quantum foam could be generating a subtle pressure, a kind of anti-gravity that drives dark energy's push against the cosmos. Quantum field theory offers a clue to how this might work. At its heart, the theory suggests that what we call empty space is actually a seething network of fields, invisible frameworks that fill every corner of reality. Even when those fields appear calm, they're never truly still. Like a pot of water heated to just below boiling, space simmers with latent energy, particles appearing and disappearing in a statistical frenzy. And just as steam can lift a lid, these fluctuations might exert an outward force on the fabric of space-time itself, yet there's a catch, one that keeps physicists awake at night. When we calculate how much energy these quantum fluctuations should contribute to the universe, the numbers are catastrophically wrong. According to theory, the vacuum's energy density ought to be enormous enough to rip atoms apart instantly. But observations show dark energy's effect is far weaker, like comparing a hurricane to a gentle breeze. This mismatch isn't just a minor hiccup, it's a glaring sign that our understanding of quantum mechanics and gravity is incomplete. Some researchers speculate that undiscovered symmetries or canceling effects might be at play, quietly taming the chaos. Others wonder if dark energy is the shadow of deeper physics, a phenomenon we're only seeing through a foggy lens. What's undeniable is the eerie resonance between the quantum and cosmic scales. The same unpredictable jitter that governs particles might also steer galaxies, bridging the infinitesimal and the infinite. It's as if the universe has hidden a secret code in the static of empty space, and cracking it could reveal why everything from atoms to galaxy clusters behaves the way it does. The deeper we probe, the clearer it becomes. The answers to the universe's biggest mysteries might be hiding in plain sight, written in the restless whispers of the quantum foam. Einstein once scribbled a number into his equations, a tiny correction he called the cosmological constant. At the time, he believed the universe was static, neither expanding nor contracting, and this mathematical fudge factor was his way of forcing the math to match that assumption. But when Edwin Hubble discovered the universe was actually stretching apart, Einstein famously called the constant his greatest blunder, tossing it aside like a failed experiment. Yet in one of science's most delicious ironies, that discarded idea came roaring back when astronomers found the expansion wasn't just happening, it was accelerating. Suddenly, the cosmological constant wasn't a mistake anymore. It was the leading candidate to explain dark energy's relentless push. But here's where the plot thickens. When physicists try to calculate how much energy the quantum vacuum should contribute to the cosmos, their equations spit out a number so absurdly large, it defies reason. 10 to the power of 120 times greater than what we actually observe. To put that in perspective, it's like predicting a single candle could outshine the entire observable universe. This isn't just a rounding error, it's the most embarrassing mismatch in the history of science. And it leaves us with a haunting question: is our math catastrophically wrong, or are we missing something fundamental about how quantum fluctuations interact with spacetime? Some theorists argue the answer lies in cancellation effects, subtle symmetries we haven't discovered yet, where positive and negative energy fluctuations almost perfectly balance out, leaving behind just a faint whisper of dark energy. Others propose even wilder ideas, like extra dimensions mopping up the excess energy or undiscovered fields that suppress the vacuum's true power. Then there's the radical possibility that gravity itself behaves differently at cosmic scales, bending the rules in ways we can't yet fathom. What makes this puzzle so thrilling is how it ties the smallest quirks of quantum mechanics to the grandest scales of the cosmos. The same math that describes particles popping in and out of existence might also hold the key to dark energy's grip on the universe. Einstein's blunder could turn out to be his greatest prophecy, a clue hidden in plain sight, waiting for us to decipher it. And as telescopes peer deeper into space and particle colliders probe finer details of the quantum world, we're inching closer to a revelation that could rewrite physics itself. The cosmological constant problem isn't just a gap in our knowledge, it's a flashing signpost pointing toward the next revolution in understanding reality. Even in the coldest depths of space, where temperatures plunge to absolute zero and atoms grind to a near standstill, there's a pulse of energy that never fades. This is zero-point energy, the universe's way of whispering that true stillness is impossible. Quantum mechanics insists that fields can never fully turn off. Like a guitar string that hums even when untouched, the fabric of reality vibrates with an irreducible minimum of energy, a background hum woven into the cosmos itself. But here's the paradox: if you add up all this zero-point energy across the infinite expanse of space, the total should be colossal enough to warp spacetime beyond recognition. Yet when we measure dark energy's actual influence, it's almost vanishingly faint. How can the math be so spectacularly wrong? One tantalizing possibility is that nature has built in symmetries, hidden balances, that cancel out most of this energy before it can shake the cosmos. Think of it like a tug of war between opposing teams, where each yank to the left is matched by an equal pull to the right. The rope barely moves, even though both sides are exerting tremendous force. Some theories suggest similar cancellations might be happening in the quantum vacuum, with particles and antiparticles or undiscovered fields neutralizing each other's energy, leaving behind only a faint residue we detect as dark energy. But there's another, even stranger idea bubbling among physicists. What if zero-point energy isn't the source of dark energy at all? What if it's more like background noise, a constant, unchanging hum that gravity simply ignores? In this scenario, dark energy could arise from something entirely different, like a new kind of field or a flaw in our understanding of how gravity works at cosmic scales. It's as if we've been trying to hear a faint melody by amplifying the static around it, missing the true music entirely. The stakes couldn't be higher. If zero-point energy really is tied to dark energy, then unlocking its secrets would mean rewriting the rules of quantum mechanics and relativity alike. We'd finally understand why the vacuum of space isn't a silent void but a dynamic, throbbing entity, one that might hold the key to the universe's ultimate fate. Until then, the discrepancy between theory and observation remains a beacon, guiding us toward a deeper truth hidden in the hum of nothingness. Imagine two thin metal plates placed so close together in a vacuum that there's barely enough room for a single atom to slip between them. According to classical physics, nothing should happen, just two silent, motionless sheets floating in empty space. But in 1848, Dutch physicist Hendrik Casimir made a startling prediction. These plates would actually be pulled together by an invisible force, as if some ghostly hand were nudging them. Years later, experiments proved him right. The plates moved, and with that, we had our first direct evidence that the quantum vacuum isn't just theoretical, it exerts real, measurable pressure on the physical world. This phenomenon, now called the Casimir Effect, reveals something profound about the nature of reality. Between those plates, only certain wavelengths of virtual particles can exist, like sound waves trapped in a tiny echo chamber. But outside the plates, the quantum foam bubbles without restriction. The result, an imbalance, a subtle pressure differential that pushes the plates together. It's as if the universe itself is leaning on them, whispering through the chaos of empty space. Now, stretch this idea to cosmic scales. If quantum fluctuations can move metal plates in a lab, could they also be nudging galaxies apart? The math suggests a tantalizing parallel. Just as the Casimir effect creates a net force by restricting particle wavelengths, dark energy might arise from the way quantum foam interacts with the expanding fabric of space-time. Picture the universe as an infinite version of that vacuum chamber, with space-time itself playing the role of the plates. Every time the cosmos grows, new room opens up for quantum fluctuations, potentially releasing energy that fuels further expansion. But here's the catch: scaling up from a lab bench to the entire universe isn't just a matter of adding zeros. The Casimir effect deals with distances smaller than a micrometer, while dark energy operates across billions of light years. Bridging that gap requires physics we don't yet have, a theory that seamlessly stitches together quantum mechanics and gravity. Some researchers speculate that exotic particles or undiscovered dimensions might mediate this connection, while others argue we're missing a fundamental principle entirely. What makes the Casimir effect so electrifying isn't just its validation of quantum weirdness, it's the door it cracks open. For the first time, we glimpse the invisible turbulence of the vacuum, not through equations but through the gentle clink of metal plates. And if that turbulence can bend the rules on microscopic scales, who's to say it isn't shaping the grandest structures in the cosmos? The answer might lie in future experiments, where physicists probe even finer scales or hunt for echoes of these effects in the large-scale structure of the universe. Until then, the Casimir effect stands as both a triumph and a teaser, a hint that the answers to our biggest cosmic questions could be hiding in the quietest corners of empty space. At first glance, dark energy and vacuum energy seem like perfect cosmic counterparts, two sides of the same coin. Both represent invisible forces woven into the fabric of space itself, both defy classical intuition, and both challenge our deepest theories of reality. But when you line up the math, the numbers tell a different story, one so baffling it's been called the worst theoretical prediction in the history of physics. The heart of the problem lies in scale. Quantum field theory suggests that every cubic centimeter of empty space should buzz with vacuum energy so intense it would curve the universe into a singularity within moments. Yet the dark energy we observe is gentle by comparison, a faint pressure barely strong enough to nudge galaxies apart over billions of years. The mismatch isn't just a rounding error, it's a factor of 10 to the power of 120. That's like expecting a candle's flicker and measuring the heat of a supernova instead. So why do some scientists still cling to the connection? Because the alternatives might be even stranger. One camp argues that unknown symmetries or cancellation mechanisms could be suppressing the vacuum's true ferocity. leaving behind only the faint echo we call dark energy. Picture a raging river dammed by invisible barriers, with just a trickle slipping through. Others propose that vacuum energy isn't static but dynamic, evolving over cosmic time in ways we haven't yet modeled. Then there's the radical fringe, physicists who suspect dark energy isn't energy at all. Modified gravity theories, like those involving extra dimensions or chameleon fields, suggest Einstein's equations might need rewriting at vast scales. In these scenarios, what we perceive as dark energy could be an illusion, a side effect of gravity behaving differently across intergalactic distances. The debate is far from academic. If vacuum energy is the true source, it implies an unimaginable fine-tuning in the laws of physics, where opposing forces balance with precision akin to stacking marbles across the Grand Canyon. If it's something else entirely, we might be standing at the brink of a paradigm shift as profound as relativity or quantum mechanics. Every new galaxy survey, every particle collision experiment inches us closer to answers, or deeper into the maze. One thing's certain, the universe loves a good puzzle, and this one's its masterpiece. Symmetry isn't just an aesthetic preference of the universe, it's the hidden scaffolding holding reality together. From the perfect spirals of galaxies to the way particles mirror each other in collisions, symmetry dictates the rules of existence. But here's the twist: when symmetries shatter, they don't just vanish. Like a cracked vase, the fragments retain echoes of their former wholeness, and those echoes might be fueling the expansion of the cosmos itself. Take the Higgs field as a cosmic example. In the early universe, this field was perfectly symmetrical, humming with untapped potential, but as temperatures cooled, that symmetry broke, releasing energy that gave mass to particles, a process akin to water freezing into ice, where the orderly structure hides the chaos of the transition. The leftover energy from that event didn't disappear, it seeped into the fabric of spacetime. Now, imagine similar symmetry breaks happening across countless quantum fields, each one leaving behind traces of energy like footprints in cosmic sand. Could dark energy be the sum of all these forgotten whispers? The math hints at something tantalizing. In particle physics, when symmetries break, they often create residual forces or energies, phenomena we've observed in everything from superconductors to the alignment of magnets. On a quantum level, these effects are fleeting and localized, but scale them up across the universe, and the collective residue might manifest as a gentle, pervasive, pushy dark energy in disguise. It's as if every broken symmetry in the quantum foam is tossing a pebble into a pond, and the ripples are stretching spacetime itself, yet mysteries loom. Why would these broken symmetries leave behind just enough energy to drive cosmic acceleration, neither too weak to notice nor so strong it tears atoms apart? Some theorists propose a delicate balancing act, where opposing symmetry breaks cancel out most of their energy, leaving only a faint, uniform haze. Others speculate that dark energy isn't static but dynamic, a relic of symmetries still shifting as the universe evolves. Picture a cosmic game of musical chairs, where each time the music stops another symmetry breaks. The leftover energy subtly reshapes the cosmos. The stakes are dizzyingly high. If broken symmetries are the key, we might finally bridge particle physics with cosmology, revealing how the tiniest quirks of quantum fields dictate the fate of galaxies. Or perhaps we're glimpsing a deeper truth, that dark energy isn't energy at all, but the shadow of spacetime's hidden architecture, a structure built on symmetries we've yet to name. Every collision in a particle accelerator, every snapshot of distant supernova brings us closer to answers, or deeper into the labyrinth. One thing's certain: the universe's love of symmetry isn't just beautiful. It might be the reason we're here to ponder it at all. What if everything we see, the stars, galaxies, even the space between them, is just an illusion? a cosmic mirage projected from some hidden surface at the edge of reality. This isn't the plot of a sci-fi movie, it's the holographic principle, a radical idea born from black hole physics that suggests our three-dimensional universe might be nothing more than information painted on a distant two-dimensional surface, like a movie projected from a flat screen. And if that sounds mind-bending, wait until you hear how this could rewrite our understanding of dark energy and quantum vacuum fluctuations. The story starts with black holes, those cosmic traps where gravity is so strong even light can't escape. In the 1970s, physicist Jacob Bekenstein made a startling discovery. A black hole's entropy, a measure of its hidden information, isn't determined by its volume, but by the area of its event horizon, the point of no return. It was as if all the complexity inside a black hole could be encoded on its surface, like a hologram storing a 3D image in 2D pixels. Decades later, string theorists took this idea further, proposing that the entire universe might work the same way, that every particle, every force, even the fabric of spacetime itself could be a projection from some vast, unseen boundary. Now here's where things get cosmic. If the holographic principle is true, it could solve one of physics' most nagging problems: why quantum vacuum fluctuations don't rip the universe apart. Remember that catastrophic mismatch between predicted and observed vacuum energy. In a holographic universe, the math changes. Information, including the energy of quantum foam, wouldn't be distributed infinitely through space but confined to a boundary, like pixels on a screen. That limitation could naturally suppress the explosive energy we'd expect, leaving behind only the faint whisper we call dark energy. But how? Imagine blowing up a balloon. As it expands, its surface stretches, thinning out any patterns painted on it. Similarly, in a holographic cosmos, as the universe grows, information encoded on its boundary would dilute, creating an effect that mimics dark energy's gentle push. The acceleration we observe might not be due to some mysterious force. It could be the natural consequence of a universe decoding itself from a distant, fading projection. The implications are staggering. If the holographic principle holds, it would mean gravity and quantum mechanics aren't separate puzzles, they're two sides of the same hologram. Quantum fluctuations wouldn't just be random noise, they'd be pixels flickering on the cosmic projector, their patterns dictating the shape of spacetime itself. And dark energy, it might be the universe's way of recalculating its own resolution as it scales up, like an image adjusting to fit a bigger screen. Of course, this isn't settled science. Critics point out that the holographic principle remains largely theoretical, with no direct experimental proof yet, but supporters counter that it's one of the few frameworks where the math doesn't explode into nonsense when you try to merge quantum physics with gravity. And as telescopes map larger swaths of the universe and supercomputers simulate ever more complex quantum systems, we might finally spot the telltale glitches, tiny inconsistencies in the cosmic code that reveal the hologram beneath the illusion. Whether the holographic principle is the key to unlocking dark energy or just another step in a longer journey, one thing's clear: the universe loves to surprise us. What seems like empty space might be teeming with hidden information, and what looks like an accelerating cosmos could be the shadow of a deeper reality, flickering into existence one pixel at a time. What if our universe's dark energy isn't a single, finely tuned accident but one winning ticket in an infinite cosmic lottery? This is the Multiverse Hypothesis, a daring idea that suggests our universe might be just one bubble in a frothing sea of realities, each with its own unique laws of physics. In some of those universes, dark energy could be so weak that gravity crushes everything into black holes before stars ignite. In others, it might be so strong that matter is ripped apart before atoms can even form. But here in this universe, the numbers just happen to line up perfectly, allowing galaxies, planets, and ultimately, curious minds to ponder why. this anthropic explanation, that we observe these specific conditions because they're the only ones that allow observers to exist, is as controversial as it is elegant. Critics argue it's a cop-out, a way to sidestep the need for deeper explanations. After all, if every possible universe exists somewhere, then of course we'd find ourselves in one that permits life. It's like walking into a library and marveling that one book happens to have your name on the cover, when in reality, every possible book already exists on the shelves. Proponents, however, counter that the multiverse isn't just philosophical hand-waving. String theory, for instance, predicts a landscape of possible universes, each with different physical constants. In this view, dark energy's value isn't a puzzle to solve but a roll of the dice we happen to win. But the multiverse idea doesn't just reset the board, it changes the game entirely. If true, it means the laws of physics we take as fundamental might be nothing more than local bylaws, quirks of our particular cosmic neighborhood. The cosmological constant problem, that staggering mismatch between predicted and observed vacuum energy, could simply be a selection effect. Universes where the numbers are even slightly different might be barren, devoid of anyone to ask the question, we're not here because dark energy is special, dark energy seems special because we're here. Yet the multiverse hypothesis raises its own thorny questions. If other universes are forever beyond our observation, can we ever test the idea scientifically? Some theorists point to subtle fingerprints patterns in the cosmic microwave background or anomalies in particle physics that might hint at collisions with other universes. Others suggest that the very fine-tuning we're trying to explain could itself be evidence, a statistical clue that we're part of something vastly larger. But until we find concrete proof, the multiverse remains a tantalizing what if, a framework that reshapes how we think about dark energy without yet delivering final answers. Whether the multiverse is the key to unlocking dark energy's mystery or just another twist in the cosmic plot, one thing's certain: it forces us to confront the sheer improbability of our existence. The universe didn't have to be this way, and yet here we are in a Goldilocks zone of physics, where the numbers align just right for life to emerge, question, and wonder. Is that coincidence, necessity, or something far stranger? The answer, if it exists, might lie beyond the edges of our reality. Picture two particles born from the same quantum event, separated by millions of light years, yet still whispering to each other instantaneously. Changing one state magically alters the other's, no matter the distance. This eerie phenomenon, quantum entanglement, defies everything we know about locality and time. Einstein famously called it spooky action at a distance, dismissing it as impossible. Yet experiments have proven it's real, leaving us with a breathtaking question: if particles can stay mysteriously connected across the cosmos, could entanglement also be stitching together the fabric of the universe itself? The answer might lie in the vacuum. Even in empty space, quantum fields are constantly entangled, their fluctuations linked in an intricate web. Normally, these connections are too fleeting and microscopic to notice. But some physicists speculate that on cosmic scales, this web might not just be background noise, it could actively shape the structure of reality. Think of spacetime as a vast tapestry, with entangled threads running through it. As the universe expanded after the Big Bang, those threads might have stretched but never snapped, imprinting quantum connections onto the distribution of galaxies, dark matter, and even dark energy. Here's where it gets wild. Simulations of the early universe suggest that large-scale structures, the cosmic web of filaments and voids we see today, might bear the fingerprints of primordial quantum entanglement. Just as entangled particles influence each other's behavior, entangled regions of spacetime could have subtly guided where matter clumped together and where it thinned out. Over billions of years, those tiny quantum preferences might have snowballed into the galaxy clusters and cosmic voids we observe. Now, zoom out further. If entanglement helps sculpt the universe's structure, could it also be tweaking dark energy's influence? One provocative idea suggests that entangled vacuum fluctuations might create a kind of quantum pressure, counteracting gravity's pull in ways we don't yet understand. Picture entangled particles as tiny springs woven into spacetime. When stretched by cosmic expansion, they could push back, adding fuel to dark energy's acceleration. It's a radical notion, but not without precedent. In black hole physics, entanglement is already known to warp spacetime in surprising ways, creating phenomena like wormholes and quantum bridges. Of course, the leap from lab-scale entanglement to cosmic-scale effects isn't simple. The biggest hurdle is scale. The entanglement we observe in labs lasts microseconds and spans millimeters, while cosmic entanglement would need to persist for billions of years across light years of space. Some theories propose that undiscovered particles or fields act as cosmic messengers, preserving these quantum links. Others suggest gravity itself might be a side effect of entanglement, a concept dubbed entanglement gravity. Whether or not entanglement holds the key to dark energy, the mere possibility reshapes how we see the universe. No longer just a collection of separate objects governed by rigid laws, the cosmos might be a vast, interconnected network, a quantum symphony where every particle, every galaxy, hums in hidden harmony. And if that's true, the greatest mysteries of the cosmos might not be in the stars or the void between them, but in the invisible threads tying it all together. Right now, dark energy is like a gentle breeze nudging galaxies apart, but what if that breeze becomes a hurricane? Some theories suggest that dark energy isn't just constant, it could grow stronger over time, morphing into something far more sinister, phantom energy. In this scenario, the universe doesn't just expand, it shreds itself apart, atom by atom, in a cataclysm cosmologists call the Big Rip. Picture this: trillions of years from now, the accelerating expansion crosses a threshold where gravity, electromagnetism, even the nuclear forces binding atoms together are overwhelmed. First, galaxies would be ripped from each other, then stars would explode away from their own planets. Finally, in the last microseconds, molecules, atoms, and even quarks would be torn asunder, leaving nothing but a cold, empty void where the universe once thrived. This apocalyptic vision hinges on the quantum vacuum's most unsettling possibility, that its energy density might not stay constant, but could instead intensify as space stretches. The math behind phantom energy is as elegant as it is terrifying. If dark energy's equation of state, a measure of how its pressure relates to its density, dips below a critical value, the vacuum's push becomes self-reinforcing. Like a snowball rolling downhill, each bit of expansion would release more energy, accelerating the process until spacetime itself can't hold together. Quantum fields, which usually fluctuate in predictable ways, might enter a runaway regime where their fluctuations grow exponentially, feeding the chaos. Yet for all its drama, the Big Rip isn't inevitable. Current observations show dark energy's strength holding steady, with no signs of the ominous uptick phantom energy requires. But the mere possibility forces us to confront a deeper question: how well do we truly understand the quantum vacuum's rules? The same fields that flicker in and out of existence in lab experiments could, under extreme conditions, behave in ways that rewrite cosmic destiny. It's like discovering a hidden lever in the universe's machinery, one we didn't know existed until we saw its shadow in the equations. The stakes couldn't be higher. If phantom energy is real, it would mean the vacuum isn't just a backdrop for the universe's story, it's an active protagonist with the power to end it. And while the Big Rip might seem like science fiction today, it's a reminder that the cosmos operates on scales and timelines beyond human intuition. The quantum fields humming beneath reality's surface don't care about our clocks or calendars, they follow their own rhythms, and if those rhythms ever sink into a crescendo, even the fabric of existence might not survive the song. So where does that leave us, staring into the abyss of uncertainty, but also armed with curiosity? Every measurement of distant supernova, every probe of the cosmic microwave background, is a step toward answering whether phantom energy is a real threat or just a mathematical ghost. And in that pursuit, we're not just studying the universe's fate, we're learning how to read the hidden language of the quantum void, one whisper at a time. What if dark energy isn't a mysterious force at all, but a sign that we've been reading gravity's handwriting wrong this whole time? That's the bold claim at the heart of modified gravity theories, where physicists dare to rewrite Einstein's equations rather than invent a new cosmic ingredient. The most famous of these challengers is modified Newtonian dynamics, a framework that suggests gravity doesn't fade as quickly over vast distances as we thought. Instead of dark energy pushing galaxies apart, Min proposes that gravity itself behaves differently on cosmic scales, creating the illusion of acceleration. The idea isn't as far-fetched as it sounds. Think of gravity like a radio signal. Close to its source, the transmission is clear and strong, but venture too far, and static creeps in. Min suggests that in the emptiness between galaxies, gravity's signal might distort in ways Einstein's relativity couldn't predict. This tweak to the rules could explain why outer stars and galaxies rotate faster than expected, a puzzle usually attributed to dark matter, and why the universe's expansion seems to speed up, no dark energy required. But here's where the theory hits turbulence. While Min elegantly solves some galactic mysteries, it struggles to explain others, like the precise patterns seen in the cosmic microwave background or the way galaxy clusters collide. Worse yet, when astronomers map the universe's large-scale structure using gravitational lensing, the results match dark energy models more closely than Min predictions. It's as if the universe is whispering one story to galaxy rotations, but shouting another through the cosmos' grand architecture, yet the debate is far from settled. Some researchers are refining Min into broader frameworks like TVS, tensor vector scalar gravity, which weave in extra fields to patch its gaps. Others point to anomalies, like certain dwarf galaxies that defy dark matter expectations, as clues that gravity's rulebook needs an update. The stakes are cosmic. If modified gravity is right, we've been chasing a phantom for decades. If it's wrong, we're left with the unsettling truth that 95% of the universe is made of stuff we can't see or explain. What makes this clash so thrilling is how it forces science to question its foundations. Every new telescope, every deeper sky survey, is a test of whether gravity bends the rules or dark energy warps them. And until one side concedes, the universe keeps its ultimate secret hidden either in the fine print of Einstein's equations or the void's invisible pulse. The universe's first moments were anything but quiet. In a fraction of a second smaller than the blink of an eye, space itself erupted outward, stretching faster than the speed of light in a phenomenon called cosmic inflation. This explosive growth smoothed the cosmos like a baker rolling out dough, erasing wrinkles and imperfections to create the eerily uniform universe we see today. But here's the twist: that same repulsive force, the one that hurled space-time apart in the beginning, might still be lurking in the fabric of reality, not as inflation anymore, but as dark energy. The parallels are too striking to ignore. Both inflation and dark energy involve a form of anti-gravity, a push against the normal pull of matter. Both seem to arise from mysterious fields permeating space. And both defy our everyday intuition about how the universe should behave. The difference: inflation was a sprint, a fleeting burst that lasted perhaps a trillionth of a second. Dark energy, by contrast, is a marathon runner, exerting its gentle pressure over billions of years. Yet if they're driven by similar mechanisms, studying one could crack the code of the other. Clues might be hiding in the cosmic microwave background, the afterglow of the Big Bang. This faint radiation bath holds snapshots of the universe when it was just 380,000 years old, its patterns frozen like fossils in ancient rock. Tiny temperature fluctuations in this microwave haze reveal where matter was slightly denser or sparser, seeds that would grow into galaxies, but they also encode echoes of inflation's quantum origins. When physicists examine these ripples at the smallest scales, they're peering into the quantum foam of the infant universe, where fluctuations in the inflaton field, the hypothetical driver of inflation, left their fingerprints. Now imagine applying that same forensic approach to dark energy. If a similar field is causing today's acceleration, its quantum jitters might imprint subtle signatures on the large-scale structure of the cosmos, ghostly patterns in the distribution of galaxies, or distortions in how light bends across the universe. Some theories even suggest that dark energy could be inflation's dying ember, a remnant of that primordial field that never fully switched off. Picture a campfire that roars to life and then settles into a slow, steady smolder, except the fire is space-time itself, and the embers are driving galaxies apart. The challenge is separating the signals from the noise. Inflation's quantum fluctuations were amplified to cosmic scales, leaving clear marks. Dark energy's effects, by contrast, are subtle and cumulative, like trying to hear a whisper in a hurricane. But next-generation telescopes and sky surveys are hunting for these whispers with unprecedented precision. If they find evidence that dark energy's push shares DNA with inflation's burst, it would mean we're not just studying two cosmic mysteries, we're seeing two faces of the same phenomenon, separated by nearly 14 billion years. Whether inflation and dark energy are distant cousins or identical twins, their connection underscores a profound truth: the universe loves recycling its greatest hits. The forces that shape the beginning might still be shaping the present, hidden in plain sight, and if we learn to read their language, we might finally understand why the cosmos accelerates and what that means for the story yet to come. The greatest embarrassment in physics isn't a failed experiment or a miscalculation, it's a number so wrong, it defies reason. When theorists calculate how much energy the quantum vacuum should contain, their equations spit out a value 10 to the power of 120 times larger than what we actually observe. That's not just a rounding error, it's like predicting a single candle could outshine every star in the observable universe. This staggering mismatch, dubbed the vacuum catastrophe, isn't just a puzzle, it's a screaming red flag that our deepest theories might be missing something monumental. At its core, the catastrophe reveals a brutal clash between quantum mechanics and gravity. Quantum field theory treats empty space as a seething foam of virtual particles, each borrowing energy from the vacuum to briefly exist. Add up all those flickering contributions, and the total energy should curve space-time into a singularity within moments. Yet when we look at the cosmos, dark energy's effect is absurdly faint, like comparing a hurricane to a gentle breeze. The universe isn't just stable, it's suspiciously stable, as if some hidden mechanism is canceling out 99.999% of the vacuum's fury. One possible escape route lies in supersymmetry, an elegant framework where every known particle has a hidden twin. In this symmetrical world, fermions and bosons, the two fundamental classes of particles, could perfectly cancel each other's vacuum energy contributions, leaving behind only a whisper. The catch: we've yet to find any proof these supersymmetric particles exist, despite decades hunting for them in colliders. It's like having a mathematical blueprint for a cosmic dampener, but no hardware to build it. Then there's the radical idea of extra dimensions. If gravity, unlike other forces, leaks into hidden spatial dimensions beyond our perception, its apparent weakness in our four-dimensional world could explain the vacuum energy discrepancy. Picture a sponge soaking up water. What seems like a flood in one dimension might barely register in another. String theory, with its 10 or 11-dimensional landscapes, offers tantalizing models where this could happen. though testing them remains a formidable challenge. But the most unsettling possibility is that we fundamentally misread the cosmos. Some theorists argue that vacuum energy doesn't gravitate the way matter does, that its pressure and density might cancel out on cosmic scales, leaving only a faint residue. Others propose dark energy isn't energy at all, but an illusion caused by our imperfect understanding of gravity over vast distances. It's like realizing the map you've been using is missing entire continents, and the ocean you thought you were sailing is just a mirage. The vacuum catastrophe isn't just a technical headache, it's a crossroads for physics. Solve it, and we might unlock a unified theory of quantum gravity. Fail, and we could be forced to scrap foundational ideas about how reality works. Every new observation, from gravitational wave detectors to quantum lab experiments, brings us closer to answers, or deeper into the maze. One thing's certain, the universe's stability isn't an accident. It's either a clue, a coincidence, or a cosmic joke we're only beginning to understand. Time moves forward, not backward, a fact so obvious we rarely question it. But what if dark energy, that mysterious force stretching the cosmos apart, is secretly tugging at time's arrow too? The link between cosmic expansion and the one-way flow of time isn't just philosophical, it's woven into the laws of thermodynamics, where entropy, the measure of disorder, always increases, creating an irreversible direction for reality. And here's the twist. Some physicists suspect dark energy might be the hidden hand guiding this process, tying the fate of time itself to the quantum vacuum's restless energy. Think of the universe like a clock winding down. In its early moments, everything was packed into a hot, dense, highly ordered state, like a pristine deck of cards fresh from the box. But as space expanded, that order unraveled, scattering matter and energy into galaxies, stars, and eventually, the chaotic void between them. This growth of entropy defines time's arrow, and dark energy's acceleration could be pouring fuel on the fire. The more space stretches, the more room there is for disorder to spread, like ink diluting in an ever-growing pool. Now, dive deeper into the quantum realm. Virtual particles flashing in and out of existence don't just fill space, they also generate entropy. Each fluctuation is a tiny burst of chaos, a microscopic contribution to the universe's disorder. Over cosmic scales, these flickers might add up to something profound, subtly nudging time's arrow forward. Some models even suggest that dark energy's push could be entropy in disguise, a cosmic scale manifestation of the vacuum's relentless churn. It's as if the universe has two clocks, one ticking with the rhythm of particles, the other with the expansion of space, and dark energy keeps them synchronized. But the plot thickens when you consider black holes. These cosmic traps devour matter and energy, creating regions where entropy skyrockets. Stephen Hawking famously showed that black holes emit radiation, slowly evaporating over eons. That process releases entropy back into the universe, but here's the catch. If dark energy keeps accelerating expansion, future black holes might vanish before they fully evaporate, leaving behind frozen remnants in an increasingly empty cosmos. Time's arrow could falter in these distant eras, with entropy hitting a ceiling, a state physicists call heat death, where the universe becomes a lukewarm sea of particles too sparse to interact. The implications are dizzying. If dark energy influences entropy, it doesn't just shape space, it sculpts time's very architecture. This could bridge two of physics' greatest theories, thermodynamics, which governs heat and work, and quantum field theory, which describes the vacuum's chaos. Imagine a cosmic feedback loop where vacuum fluctuations generate entropy, entropy drives time's arrow, and time's flow determines how dark energy reshapes the universe. It's a dance spanning from the tiniest particles to the vast cosmic web, all moving to the same hidden rhythm, yet mysteries remain. Why does entropy's rise align so neatly with cosmic expansion? Is dark energy actively speeding up time's flow, or is their connection a cosmic coincidence? The answers might lie in future experiments probing the quantum vacuum's entropy or simulations of universes with different dark energy strengths. Until then, one thing's clear: the universe isn't just expanding, it's evolving, and every second that ticks by carries the fingerprint of the void's invisible hand. Imagine a river so perfectly smooth that it flows without ripples or resistance, where even the tiniest object could glide forever without slowing down. This isn't a fantasy, it's the real-world behavior of superfluids, exotic states of matter where friction vanishes entirely. Now, stretch that idea to cosmic scales. What if the quantum vacuum itself, the so-called empty space between stars, isn't just a chaotic foam of particles, but a superfluid so vast and subtle that its flawless flow shapes the expansion of the universe? This isn't just a poetic metaphor. Superfluid vacuum theory, a bold offshoot of quantum physics, suggests that the vacuum's seething energy might organize itself into a cosmic-scale superfluid, with properties eerily similar to liquid helium cooled to near absolute zero. In labs, superfluids defy gravity, creep up walls, and form vortexes that spin without slowing down. If the vacuum shares these traits, it could explain why dark energy's push is so uniform, like a frictionless tide lifting every galaxy in sync. The math behind this idea is as elegant as it is speculative. In a superfluid vacuum, quantum fluctuations wouldn't just be random noise, they'd behave like collective waves in an ultra-stable medium. This could suppress the wild energy swings predicted by traditional quantum field theory, leaving behind only the gentle, pervasive pressure we call dark energy. Think of it like the difference between a stormy ocean and a glassy lake. Both contain water, but one's chaos is tamed by deeper forces. Critics point out the hurdles. Superfluids on Earth require extreme cold and specific conditions to form. How could the vacuum, filled with high-energy fluctuations, mimic such delicate order? Proponents counter that the universe's sheer size might play a role. Statistical smoothness emerging from quantum chaos, like how individual water molecules create a compound when viewed from afar. Others speculate that hidden symmetries or undiscovered particles could act as cosmic refrigerants, cooling the vacuum into this exotic state. Yet the most tantalizing clue comes from black holes. Some models suggest that space-time near a black hole's event horizon behaves like a superfluid, with quantum information flowing seamlessly across its surface. If true, this could mean superfluidity isn't just a local oddity, but a fundamental feature of space-time itself, one that's been hiding in plain sight, sculpting the universe's expansion all along. Whether the superfluid vacuum theory holds up or not, it's a reminder of how creatively physics probes the unknown. Sometimes the answers to the cosmos' biggest mysteries aren't found in new particles or forces, but in reimagining the fabric of reality itself, as a river without banks, a sea without shores, or a void that's anything but empty. Black holes aren't just cosmic vacuum cleaners, they might be the universe's most unexpected dark energy laboratories. These gravitational monsters, where space-time bends so severely that not even light escapes, have long been studied for their ability to crush matter into oblivion. But recent theories suggest they could also be whispering secrets about the quantum vacuum and the mysterious force pushing galaxies apart. Take Hawking radiation, the faint glow predicted to emanate from black holes as they slowly evaporate. This phenomenon arises directly from quantum fluctuations at the event horizon, the point of no return where virtual particles get torn apart, with one falling in and the other escaping as radiation. If these fleeting vacuum fluctuations can influence a black hole's lifespan, could they also be shaping dark energy's grip on the cosmos? The connection gets even stranger when you consider how black holes evolve over cosmic time. As the universe expands due to dark energy, black holes aren't just passive bystanders, they're growing. Supermassive black holes at the centers of galaxies feed on surrounding gas and stars, but they might also absorb energy from the expanding space itself. Some models propose that this process could subtly alter the vacuum's behavior near black holes, creating localized ripples in dark energy's effects. Picture a stone dropped into a pond. The water's surface represents the quantum vacuum, and the stone's splash distorts the otherwise uniform ripples. Black holes might be doing something similar on a cosmic scale, warping the fabric of dark energy in their vicinity. Then there's the mind-bending idea that black holes could be cosmic batteries, storing vacuum energy in their unfathomably dense cores. According to certain interpretations of quantum gravity, the singularity at a black hole's heart might not be a point of infinite density, but a knot of ultra-condensed vacuum fluctuations. If true, this would mean black holes aren't just consumers of matter and energy, they are transformers, converting the chaotic jitters of the quantum foam into something more structured. It's like compressing static into a coherent signal, and that signal might be subtly influencing the universe's expansion rate, but the real bombshell comes from holographic principles, which suggest that all the information inside a black hole is encoded on its two-dimensional surface. If that's the case, then the vacuum fluctuations near the event horizon aren't just random noise, they're pixels in a cosmic code, a projection of deeper physics. Some theorists argue that this holographic interplay between surface and volume could be the key to understanding why dark energy's strength is so finely tuned. The same mathematical tricks that prevent black holes from violating the laws of thermodynamics might also be keeping the vacuum's energy in check across the universe. Of course, these ideas are still speculative, and black holes aren't exactly easy to study up close, but upcoming telescopes like the Laser Interferometer Space Antenna LISA will listen for gravitational waves from merging supermassive black holes, potentially revealing how they interact with the expanding space around them. Meanwhile, lab experiments simulating black hole physics using sound waves or ultra-cold atoms could offer clues about how vacuum fluctuations behave in extreme gravity. Whether black holes are dark energy's accomplices, its regulators, or just innocent bystanders, their role in this cosmic drama is far from settled, but one thing's certain: in the search for answers, these gravitational behemoths are more than just monsters, they're messengers, carrying encrypted notes from the frontier where quantum mechanics and spacetime collide. And if we learn to decode their signals, we might finally understand why the universe refuses to sit still. We exist in a universe where the numbers just happen to line up perfectly. The strength of dark energy, the balance of fundamental forces, the exact conditions needed for stars, planets, and life, it's as if the cosmos rolled a trillion-sided die and landed on the one outcome that allows us to be here asking the question. This eerie fine-tuning is the heart of the anthropic principle, the idea that the universe's laws must, by necessity, permit observers to exist within it. And when it comes to dark energy, the implications are staggering. Consider this: if dark energy were even slightly stronger, just a few decimal places different in its value, the universe would have expanded so rapidly after the Big Bang that matter could never have clumped together to form galaxies, let alone stars or planets. No galaxies, no stars, no planets, no us. On the other hand, if dark energy were weaker, gravity might have reversed cosmic expansion long ago, collapsing everything back into a fiery crunch before life had a chance to emerge. The fact that we're here to measure dark energy at all suggests something profound. Its value isn't random, it's a prerequisite for our existence, but this raises a thorny question. Is dark energy's precise tuning a happy accident, or does it hint at something deeper? One camp argues for the multiverse, a vast, perhaps infinite ensemble of universes, each with different physical constants. In most of those universes, the numbers don't line up right and no life arises, but in a rare few like ours, the dice roll just right. We find ourselves in a Goldilocks zone not because the universe was designed for us, but because we couldn't exist anywhere else. It's like winning the cosmic lottery, except the prize is reality itself. Others push back, insisting the multiverse is a philosophical sleight of hand, an untestable idea that replaces one mystery with another. They argue for a deeper law, some undiscovered symmetry or mechanism that naturally sets dark energy's value to the tiny, life-friendly number we observe. After all, nature loves patterns. The way particles pair up, the way forces balance. Maybe dark energy's value isn't arbitrary, but dictated by a principle we haven't yet uncovered. Then there's the radical middle ground. Some theorists suggest that dark energy isn't a fixed constant at all, but a dynamic field evolving over time. In this view, its current value isn't a cosmic coincidence, but the result of a slow, inevitable settling into equilibrium, like a ball rolling to the bottom of a valley. If true, life arises not because of a fluke, but because the universe naturally trends toward conditions that allow it. The anthropic principle doesn't solve the dark energy puzzle, it reframes it. Instead of asking why the numbers are what they are, we're forced to confront why we're here to notice them at all. It's a humbling reminder that our search for cosmic truths is inseparable from our own existence. Every measurement, every theory, is filtered through the narrow window of a universe that allows us to be, and whether that's a clue, a constraint, or just a cosmic stroke of luck, one thing's certain: the answers we seek might be written not just in the stars, but in the very fact that we're here to read them. Studying dark energy and quantum vacuum fluctuations is like trying to catch smoke with your bare hands. The harder you grasp, the more elusive it becomes. These phenomena fill every corner of the universe, yet they leave no fingerprints, no trails, no direct traces for our instruments to capture. So how do we measure the immeasurable? Scientists have gotten creative, building tools that don't just look for dark energy or quantum fluctuations themselves, but for the subtle shadows they cast on everything around them. Take the Large Hadron Collider, for example. By smashing particles together at nearly the speed of light, this underground behemoth recreates conditions similar to the early universe, a time when quantum fluctuations were the dominant architects of reality. While we can't observe dark energy directly in these collisions, we can study the behavior of fundamental forces and particles, searching for anomalies that might hint at hidden fields or extra dimensions tied to the vacuum's energy. It's like reconstructing a crime scene from scattered clues. Even if the culprit vanishes, the evidence left behind can tell a compelling story. Then there's the Dark Energy Survey, a sprawling astronomical project that maps millions of galaxies across the sky. By precisely measuring how these galaxies cluster and move, researchers can trace the invisible hand of dark energy tugging at the cosmos. Think of it like watching leaves floating on a river. You might not see the current itself, but the way the leaves drift reveals the water's hidden flow. Similarly, the slight distortions in starlight caused by gravitational lensing, where massive objects bend space like a funhouse mirror, provide another indirect glimpse into how dark energy warps the universe's geometry over time. But perhaps the most audacious efforts are those probing the quantum vacuum itself. In labs around the world, physicists use ultra-sensitive instruments like cryogenic particle detectors or Casimir force microscopes to measure the faintest whispers of quantum fluctuations. These experiments operate at temperatures just fractions of a degree above absolute zero, where the chaotic buzz of everyday matter quietens enough to hear the universe's underlying hum. Some even hunt for hypothetical particles like actions or chameleons, which could act as cosmic messengers between the quantum realm and dark energy's large-scale effects. The challenge isn't just technical, it's philosophical. How do we test theories about things we can't touch or see? the answer lies in the universe's interconnectedness. Dark energy might be invisible, but its influence isn't. Quantum fluctuations might vanish in an instant, but their cumulative effects ripple across billions of years. By stitching together clues from particle physics, cosmology, and quantum experiments, we're slowly assembling a mosaic of the unseen, and with next-generation tools like the James Webb Space Telescope and future gravitational wave observatories, the picture is only getting clearer. The irony is delicious. To study the void, we have to pay attention to everything but the void itself. The next decade promises to be the most revealing chapter yet in our quest to understand dark energy. With missions like the Euclid Space Telescope and the Vera Rubin Observatory coming online, we're not just peering deeper into the cosmos, we're building the most detailed maps of dark energy's fingerprints ever attempted. Euclid, launched by the European Space Agency, will survey billions of galaxies across 10 billion light-years of space, measuring how their shapes and positions warp under the influence of dark energy's push. Imagine tracing the outline of a shadow you've only ever sensed before finally giving form to the formless. Meanwhile, the Vera Rubin Observatory in Chile will take this hunt to another level. Its massive mirror and cutting-edge camera will scan the entire southern sky every few nights, creating a time-lapse movie of cosmic expansion on an unprecedented scale. By tracking subtle changes in how galaxy clusters move and evolve over time, it could reveal whether dark energy's strength has varied across cosmic history, a clue that might crack open entirely new theories about its origin. Think of it like watching a forest grow over centuries to deduce the invisible forces shaping its roots, but these missions aren't working alone. NASA Nancy Grace Roman Space Telescope, set to launch later this decade, will complement their efforts by studying the cosmic microwave background, the afterglow of the Big Bang, for echoes of dark energy's early influence. Together, this trio forms a kind of cosmic detective squad, each approaching the mystery from a different angle. Euclid maps the large-scale structure, Vera Rubin tracks motion over time, and Roman probes the primordial seeds. It's the most coordinated assault on dark energy secrets we've ever mounted. What makes this moment so electrifying isn't just the technology, it's the potential for surprise. Every time we've built a better tool to study the universe, we've stumbled onto something utterly unexpected. Hubble revealed accelerating expansion. Planck mapped the microwave background with stunning precision. Now, these next-generation instruments could uncover anomalies that force us to rewrite the textbooks. Maybe dark energy isn't constant after all, but ebbs and flows like a cosmic tide. Maybe it interacts with dark matter in ways we've never imagined, or perhaps we'll find signatures of entirely new physics, extra dimensions, modified gravity, or fields beyond the standard model. The stakes couldn't be higher. If these missions confirm dark energy as Einstein's cosmological constant, it would cement one of the most profound fine-tunings in nature. If they find its dynamic, we might be staring at evidence of a universe far stranger than we thought, and if they uncover nothing, if the data stubbornly refuses to fit any existing model, well, that's when things get really interesting. Because in science, the most exciting answer isn't "we figured it out," it's "we have no idea what's going on, and now we need to rethink everything." One thing's certain, the universe hasn't finished surprising us. As these telescopes turn their gaze skyward, they're not just collecting data, they're opening a portal to the next great revolution in physics. And somewhere in the torrent of numbers and images they'll beam back to Earth, there might be a single, fleeting clue, a cosmic breadcrumb, leading us closer to the truth about the void's invisible hand. At the heart of modern physics lies a rift so deep, it threatens to split our understanding of reality in two. On one side stands quantum mechanics, governing the chaotic dance of particles smaller than atoms. On the other, Einstein's general relativity paints spacetime as a smooth, bending fabric sculpted by massive objects. Both theories work flawlessly in their own domains, yet when they collide, the math explodes into nonsense. This is the quantum gravity conundrum, and dark energy might be the Rosetta Stone that finally deciphers it. Consider the vacuum's energy for a moment. Quantum field theory calculates it by summing every possible particle fluctuation, a process that should generate enough energy to warp spacetime beyond recognition. Yet relativity treats spacetime as continuous and unaffected by these quantum jitters at cosmic scales. The result, that infamous mismatch of 10 to the power of 120, a number so preposterously wrong it screams that we're missing a fundamental bridge between these two worlds. String theory offers one tantalizing pathway. Imagine every particle isn't a point but a tiny, vibrating string, with different harmonies corresponding to different forces and particles. In this framework, gravity emerges naturally from the string's vibrations, potentially reconciling it with quantum mechanics. Some string models even suggest dark energy could arise from how these strings interact with extra, curled-up dimensions, hidden layers of reality too small to see. Picture a guitar string pressed against a fret. The note changes based on where you press. Similarly, strings vibrating in higher dimensions might produce effects we perceive as dark energies push. Then there's loop quantum gravity, string theory's scrappy rival. Instead of strings, it proposes spacetime itself is woven from microscopic, interwoven loops, a pixelated fabric where gravity and quantum effects unite. In this view, dark energy could be the leftover tension from spacetime's quantum weave, like the faint hum of a stretched rubber band. Unlike string theory's extra dimensions, loop quantum gravity keeps reality firmly in 4 dimensions, but reimagines its structure at the tiniest scales. Both approaches share a common goal: to quantize gravity, treating it not as a smooth force but as something made of discrete, indivisible chunks. The stakes couldn't be higher. If either theory succeeds, it wouldn't just solve the vacuum energy catastrophe, it could reveal why dark energy's value is so eerily fine-tuned for life. Maybe the answer lies in how quantum gravity imposes hidden symmetries, canceling out most of the vacuum's chaos, or perhaps dark energy is a side effect of spacetime's quantum structure, emerging naturally from equations we haven't yet written. What makes this search so electrifying is how it turns the problem inside out. Instead of asking why quantum mechanics and relativity don't fit, we're forced to ask, what deeper reality are they both approximating? Every unexplained cosmic phenomenon, from dark energy's acceleration to black hole singularities, might be clues written in a language we're only beginning to learn. And when we finally crack the code, we won't just understand the universe's expansion, we'll glimpse the hidden grammar of existence itself. Neutrinos are the universe's ultimate ghosts, particles so elusive they pass through entire planets like they're not even there. Born in the hearts of stars, supernova, and even the Big Bang itself, these tiny, nearly massless particles outnumber atoms in the cosmos by billions to 1. Yet despite their abundance, they've long been thought of as cosmic bystanders, barely interacting with anything. But what if we've underestimated them? New research suggests these phantom particles might be quietly shaping the expansion of the universe itself, threading a subtle connection between the quantum world and dark energy's grand influence. Take their mass, for instance. For decades, neutrinos were assumed to be weightless, zipping through space at the speed of light. Then, in the late 1990s, experiments revealed something startling. They do have mass, albeit vanishingly small. A single neutrino's mass is less than a millionth of an electron's, but multiply that by the trillions passing through your body every second, and suddenly, their collective gravitational pull becomes impossible to ignore. Some cosmologists argue this could tweak the universe's expansion rate, like a whisper nudging a pendulum, but the real intrigue lies in how neutrinos might interact with dark energy's mysterious field. One provocative theory suggests that as the universe expands and neutrinos lose kinetic energy, their fading momentum could subtly alter the vacuum's behavior, amplifying or dampening dark energy's push. Picture a boat gliding across a lake. The wake it leaves behind changes the water's surface long after it's passed. Neutrinos might be creating a similar ripple in spacetime's fabric, their gradual slowdown leaving faint imprints on how dark energy evolves. There's also the tantalizing possibility that neutrinos and dark energy share a deeper kinship. Certain extensions of the Standard Model propose that neutrinos could interact with hypothetical particles called quintessence fields, the same kind often invoked to explain dark energy's properties. If true, this would mean neutrinos aren't just passive travelers, but active players in the cosmos's expansion, their behavior intertwined with the vacuum's hidden dynamics. It's like discovering that a background actor in a play has secretly been pulling the stage's curtains all along. Of course, proving any of this is a monumental challenge. Neutrinos are notorious for dodging detection. It takes detectors the size of office buildings buried deep underground to catch even a handful, yet next-generation experiments like DUNE, Deep Underground Neutrino Experiment, aim to track their properties with unprecedented precision, potentially spotting anomalies that hint at dark energy's influence. Meanwhile, astronomers are scouring the cosmic microwave background and large-scale galaxy distributions for patterns that might reveal how neutrinos have sculpted the universe's growth. Whether neutrinos are cosmic puppeteers or just bit players in the dark energy saga, their story reminds us of a profound truth: the universe's biggest mysteries often hide in its smallest details. From the quantum flutter of a single particle to the relentless stretch of spacetime, everything is connected, and sometimes, the faintest whispers carry the loudest echoes. Imagine the ground beneath your feet suddenly turning to air, not just collapsing, but transforming into something entirely different, rewriting the rules of reality itself. That's the spine-chilling premise of vacuum decay, a hypothetical doomsday scenario where the quantum vacuum, the very fabric of space, could spontaneously unravel. Here's how it would work. Our universe's vacuum isn't necessarily the lowest energy state possible. Like a marble resting in a shallow dent on a hillside, it might be metastable, seemingly stable, but with the potential to roll into a deeper valley if given the right nudge. If that happens, a bubble of true vacuum could form, expanding at the speed of light, rewriting physics as it goes. One moment stars, planets, and life exist, the next they're erased, replaced by a new reality with different fundamental forces, particles, and laws. This isn't just speculative fiction. The math behind vacuum decay comes straight from quantum field theory, the same framework that predicts particles like the Higgs boson. The Higgs field, which gives particles mass, is thought to be metastable, a conclusion drawn from its measured properties at the Large Hadron Collider. If the field's potential energy curve resembles a roller coaster with a precarious peak, even a random quantum fluctuation could tip it over the edge. The terrifying part, unlike other cosmic threats, asteroids, supernova, even black holes, vacuum decay would offer no warning. The bubble's edge would arrive before any light or signal could herald its approach. But before you panic, consider the scale of unlikely. The estimated timescale for such an event is longer than the current age of the universe by many orders of magnitude. Nature's dice would need to roll a perfect catastrophe, and so far, the cosmos seems content to keep rolling snake eyes. Still, the mere possibility raises profound questions. Why is our vacuum so precariously balanced? Some theorists argue this fragility is a side effect of the fine-tuning that allows life to exist, a cosmic trade-off where stable vacuums might lack the necessary conditions for complexity. Others propose undiscovered physics that stabilizes the vacuum, like hidden symmetries or higher dimensional effects. The most unsettling implication isn't the doom itself, but what it says about our place in the cosmos. If vacuum decay is possible, even improbable, it means the universe isn't just indifferent to life, it's fundamentally unstable, a house of cards built on quantum uncertainty. Yet here we are, thinking, measuring, and wondering, in the brief window before the dice might roll against us. That tension between cosmic fragility and the resilience of existence is what makes vacuum decay more than a physics puzzle. It's a mirror held up to the universe's deepest mysteries, revealing how little we truly know about the ground beneath our feet and the void beyond. What if the key to understanding dark energy isn't buried in equations or particle collisions, but in the very geometry of reality itself? Enter the holographic dark energy model, a radical idea that reimagines the cosmos not as a three-dimensional volume, but as a two-dimensional surface encoded with all the information needed to reconstruct our universe. This isn't science fiction, it's a serious hypothesis rooted in black hole physics, where the entropy of a black hole, its hidden information, isn't determined by the space inside it, but by the area of its event horizon. If that principle holds for the entire universe, it could rewrite how we think about dark energy's grip on cosmic expansion. Here's the core insight: in a holographic universe, the vacuum's energy density wouldn't scale with volume, the traditional way we calculate energy in space, but with surface area. Picture a room covered in wallpaper. The patterns on the walls don't fill the room, they're confined to its edges. Similarly, holographic dark energy suggests that the vacuum's energy isn't spread evenly through space, but is instead encoded on a cosmic boundary we can't yet perceive. This geometric twist could explain why dark energy's observed value is so absurdly tiny compared to quantum field theory's predictions. The math doesn't explode into nonsense because the universe isn't adding up infinite contributions from every point in space, it's tallying finite data on a distant, two-dimensional screen. The implications are staggering. If true, this model would solve the cosmological constant problem, that infamous factor of 10 to the power of 120 mismatch, by fundamentally changing how we account for vacuum energy. Instead of summing every quantum fluctuation in 3 dimensions, we treat them as projections from a lower dimensional surface, where their cumulative effect is naturally suppressed. It's like swapping a cacophonous orchestra for a solo pianist, the same notes, but far less chaotic. But how do we test such an abstract idea? The answer lies in the universe's expansion history. Holographic dark energy predicts a subtle but measurable difference in how the acceleration rate changes over time compared to standard models. Upcoming telescopes like Euclid and the Vera Rubin Observatory will scrutinize these cosmic timelines, hunting for deviations that might favor the holographic approach. Another clue could come from the large-scale structure of the cosmos. If dark energy's influence is tied to surface area rather than volume, its effects on galaxy clustering and cosmic voids might carry unique geometric fingerprints. Critics argue the model raises its own puzzles. What exactly is this cosmic surface, and where is it located? Some theorists propose it's the boundary of the observable universe, while others speculate it's a mathematical construct woven into spacetime's fabric. There's also the challenge of reconciling holography with quantum gravity, a hurdle even string theory and loop quantum gravity haven't fully cleared. Yet the holographic dark energy model embodies the boldest spirit of theoretical physics, reimagining reality's foundations to solve its deepest riddles. Whether it survives future tests or not, it forces us to confront a mind-bending possibility that the universe's most mysterious force might not live in the space around us, but on the edges of perception itself, where dimensions blur and information reigns supreme. And if that's true, the answers we seek might not be hidden in the void's depths, but on the cosmic equivalent of a scratch and sniff sticker, a surface that holds the scent of the entire universe. Dark matter and dark energy might sound like cosmic siblings, both invisible, both mysterious, both shaping the universe in ways we can't ignore, but here's the twist, they couldn't be more different in how they behave. Dark matter clumps together, its gravitational pull sculpting galaxies into being, while dark energy stretches space itself, pushing galaxies apart, yet together they make up 95% of the universe's total mass energy budget. So why do these two cosmic heavyweights seem to act like strangers, even though they're neighbors in the same cosmic house? The answer might lie in the quantum realm, where fields we've yet to discover could be pulling the strings behind both phenomena. Take actions for example. These hypothetical particles are leading candidates for dark matter, but they're also born from quantum field theory, the same framework that describes the vacuum fluctuations potentially linked to dark energy. Actions arise from a symmetry-breaking event in the early universe, like cosmic wrinkles frozen into the fabric of reality. If they exist, they could form invisible clouds around galaxies, explaining dark matter's gravitational grip. But here's where it gets intriguing. Some theories suggest actions might also interact with the same fields that drive dark energy's expansion, creating a subtle feedback loop between the two. Picture a seesaw where one side is matter's pull, the other is space's push, and the pivot point is a quantum field we've yet to detect. Then there's the chameleon field hypothesis, a daring idea that tries to explain both mysteries in one stroke. This theoretical field changes its properties based on its surroundings, acting like dark matter in dense regions like galaxies, but morphing into dark energy in the void between them. It's as if the universe has a shape-shifter woven into its fabric, playing dual roles to maintain cosmic balance. The chameleon field's behavior is governed by quantum mechanics, meaning its fluctuations could be the hidden thread tying dark matter's structure to dark energy's acceleration. But the plot thickens when you consider their cosmic timelines. Dark matter dominated the universe's early years, its gravity pulling matter into the galaxies and clusters we see today. Dark energy, on the other hand, only took the lead about 5 billion years ago, when the universe had expanded enough for its repulsive push to overcome gravity's grip. This handoff from matter-dominated to energy-dominated eras isn't just a historical curiosity, it's a clue. Some models propose that dark matter's gradual dilution as the universe expanded might have triggered dark energy's rise, like a hidden seesaw tipping the scales. The stakes couldn't be higher. If dark matter and dark energy share a quantum origin, it would mean we're not just solving two puzzles, we're holding a single key that unlocks both. Next-generation experiments like the Large Synoptic Survey Telescope and the Euclid space mission are hunting for subtle correlations between the distribution of dark matter and the rate of cosmic expansion, searching for fingerprints of this hidden connection. Meanwhile, particle colliders are probing ever higher energies, hoping to spot actions or other exotic particles that might bridge the gap. What makes this search so electrifying is the possibility of a grand cosmic unification. The same quantum fields that birthed particles in the early universe might still be at work today, their whispers shaping everything from the smallest galaxies to the largest voids. And if we learn to listen, we might finally hear the universe's deepest secret, that its greatest mysteries aren't separate at all, but notes in the same quantum symphony. The universe's first moments were a fireworks display of cosmic proportions, a burst of expansion so violent it makes today's accelerating universe seem sluggish by comparison. This inflationary epoch, lasting just a fraction of a second after the Big Bang, saw space itself stretching faster than light, smoothing wrinkles in the cosmos and planting the seeds for everything to come. But what powered this spectacular growth spurt? The answer might lie in the same quantum chaos that could be driving dark energy today, a thread connecting the universe's birth to its present acceleration through the restless energy of empty space. Picture a quantum field permeating the infant universe, thick with potential energy like a coiled spring. As this inflated field decayed from its high-energy state, it released a repulsive force that sent spacetime ballooning outward. But here's the fascinating part: quantum fluctuations in that field didn't just fade away, they were stretched to cosmic scales, becoming the density variations that later grew into galaxies and galaxy clusters. It's as if the universe's largest structures were born from the tiniest quantum shivers, frozen into the fabric of reality during inflation's explosive expansion. Now fast forward 14 billion years, dark energy's gentle push seems like a faint echo of inflation's roar, yet the underlying mechanism might share startling similarities. Both phenomena involve fields filling space with repulsive energy, both seem to arise from the vacuum's hidden properties, and both challenge our intuition about how empty space should behave. The critical difference: inflation was a temporary phase, a cosmic sprint that ended when its driving field decayed. Dark energy, by contrast, appears persistent, like a marathon runner maintaining a steady pace across billions of years. This parallel raises a tantalizing question: could dark energy be inflation's quieter cousin, powered by a similar quantum process operating at a different scale? Some theories suggest the inflated field never fully vanished, that a remnant of its energy lingered, too weak to notice until the universe expanded enough for its cumulative effects to dominate over gravity. Imagine a campfire that blazes brightly before settling into glowing embers. The embers might seem insignificant at first, but given enough time and space, their warmth becomes undeniable. Support for this idea comes from the universe's large-scale structure. The same quantum fluctuations that seeded galaxy formation during inflation might also imprint subtle patterns on dark energy's distribution today. Upcoming telescopes like the Vera Rubin Observatory will map these patterns with unprecedented precision, hunting for correlations that could link the two epochs. Another clue might lie in gravitational waves, ripples in spacetime, from the early universe that could carry signatures of inflation's quantum origins. If similar waves are detected from later cosmic periods, they might reveal whether dark energy's push shares the same underlying physics, yet the comparison isn't perfect. Inflation's energy density was enormous, enough to double the universe's size every tiny fraction of a second. Dark energy's density, by contrast, is minuscule, barely detectable until averaged across cosmic voids. This discrepancy leads some theorists to propose that dark energy arises from a different field altogether, one that's been quietly active since the beginning, only revealing its influence as the universe grew sparse enough for its effects to dominate. Others suggest that both phenomena stem from a deeper, unified framework where the vacuum's energy can manifest differently depending on the cosmic era. The stakes of this puzzle extend far beyond academic curiosity. If inflation and dark energy share quantum roots, it would mean the universe operates by a remarkably consistent playbook, using similar mechanisms to shape its beginnings and its long-term evolution. This symmetry could point toward a grand unified theory connecting quantum mechanics with gravity, one of physics' holy grails. Alternatively, if they're fundamentally distinct, we might be staring at evidence of multiple independent fields woven into spacetime, each taking center stage at different cosmic acts. What makes this investigation so thrilling is how it turns the cosmos into a time machine. By studying dark energy's subtle effects today, we're peering back toward the universe's first moments, searching for echoes of that primordial explosion in the void's quiet hum. And if we find them, it won't just solve two mysteries at once, it will reveal that the universe's birth and its distant future are bound together by the same quantum whispers, resonating across the eons. Even in the deepest void of space, particles can emerge from pure nothingness, not through magic, but through the raw instability of the quantum vacuum. These virtual particles, usually flickering in and out of existence too quickly to measure, can be yanked into reality under extreme conditions, like the gravitational jaws of a black hole. This phenomenon, known as Hawking radiation, reveals something profound. The vacuum isn't just empty space, it's a seething reservoir of potential matter and energy, waiting for the right cosmic trigger to unleash it. But if black holes can coax particles into existence from the void, could the universe itself be doing the same thing on a grander scale, feeding dark energy's expansion by tapping into this hidden wellspring? The process works like cosmic alchemy. Normally, virtual particle pairs, matter and antimatter, annihilate each other almost instantly, borrowing energy from the vacuum and repaying it before the universe notices the debt. But near a black hole's event horizon, one particle might fall in while the other escapes, becoming real in the process. The black hole pays the energy cost, effectively evaporating over time. Now zoom out to the entire cosmos. Some theories suggest that spacetime's accelerating expansion could create a similar energy debt, stretching quantum fields until virtual particles are pulled apart before they can annihilate. If true, this could mean dark energy isn't just a passive background force, it might actively recruit particles from the vacuum, converting quantum potential into kinetic energy that drives galaxies apart. This idea ties into one of cosmology's most daring proposals, the creation field hypothesis. Just as inflation in the early universe is thought to have generated particles from the vacuum's energy, dark energy might be doing something similar today, albeit at a far gentler pace. Picture a cosmic conveyor belt where spacetime's stretch separates virtual pairs, leaving behind a faint drizzle of real particles. Over billions of years, this trickle could add up, subtly altering the vacuum's energy density and tweaking the rate of cosmic acceleration. It's a feedback loop where expansion begets matter, and matter influences expansion, a dance between the infinitesimal and the infinite, yet the math is far from settled. Quantum field theory suggests that particle creation in an expanding universe should be negligible, a drop in the ocean compared to dark energy's observed strength. But what if we're missing a piece of the puzzle? Certain extensions to the standard model, like theories involving extra dimensions or undiscovered fields, predict enhanced vacuum particle production at cosmic scales. Others propose that dark energy interacts with these newborn particles in ways we haven't yet modeled, like a hidden hand shaping the vacuum's output to fit its needs. The implications are staggering. If particle creation fuels dark energy, it would mean the universe is literally building itself as it expands, weaving new threads into the cosmic fabric from the raw material of empty space. This wouldn't just solve the mystery of dark energy's persistence, it would redefine nothingness itself. The vacuum would no longer be a static backdrop, but an active participant, a factory humming with latent potential. And every galaxy racing away from us would carry the signature of this quantum assembly line, proof that even in the void, there's no such thing as true emptiness. Of course, testing this idea is a monumental challenge. Detecting these hypothetical particles would require instruments sensitive enough to spot a handful of quantum needles in a cosmic haystack. But next-generation gravitational wave detectors and ultra-precise cosmic microwave background measurements might one day catch whispers of this process, revealing whether the universe's expansion is truly a solo act or a duet with the quantum vacuum. Until then, the possibility lingers. Dark energy might not just bend space-time, it might be rewriting the rules of existence itself, one particle at a time. For over a century, physics has operated with four fundamental forces: gravity holding planets in orbit, electromagnetism binding atoms, and the strong and weak nuclear forces operating within atomic nuclei. But what if there's a fifth player in this cosmic game, one we've overlooked because its effects only become obvious across the vast emptiness between galaxies? This is the radical premise behind the fifth force hypothesis, a bold attempt to explain dark energy not as some mysterious property of space itself, but as the work of an undiscovered fundamental interaction. Unlike the other forces, this hypothetical fifth force wouldn't diminish with distance, it would grow stronger as space stretches, perfectly mirroring dark energy's accelerating push. Picture a rubber band connecting two galaxies. As the universe expands, the band stretches but doesn't weaken. Instead, its tension increases, adding more pull. Some models suggest this force could be carried by an exotic particle, perhaps a cousin to the Higgs boson, that interacts so weakly with normal matter we've yet to detect it. Others propose it might only switch on in the near-perfect vacuum of intergalactic space, hiding from our Earth-bound experiments. The hunt for this elusive force is already underway in laboratories around the world. Precision instruments measuring the gravitational attraction between objects at microscopic distances are searching for deviations from Newton's inverse square law, tiny anomalies that could betray a fifth force's presence. One experiment uses a hollow metal sphere suspended in vacuum, monitoring its movement for unexplained tugs. Another employs vibrating crystals so sensitive they could detect a force 1 billion times weaker than gravity. Even the slight wobble of neutron stars could carry clues, their spins potentially influenced by this hidden interaction threading through space. Yet the fifth force hypothesis isn't without its paradoxes. If such a force exists, why doesn't it alter the orbits of planets or the structure of atoms? One compelling solution suggests it might be screened in high-density environments, like a chameleon changing colors. This force could weaken dramatically near massive objects, explaining why we only notice its effects in the cosmic voids. This screening mechanism would make the force effectively invisible on Earth, while allowing it to dominate the emptiness between galaxies, exactly where dark energy's influence shines through. The implications of discovering a fifth force would rewrite physics textbooks overnight. It could provide the missing link between quantum mechanics and gravity, offer a natural explanation for dark energy's fine-tuning, and even hint at higher dimensions where this force originates. Or it might remain forever beyond our grasp, its effects blending seamlessly with the vacuum's properties, a cosmic prankster leaving just enough clues to tease us, but never enough to catch. Whether real or just a mathematical mirage, the fifth force hypothesis proves one thing: when it comes to the universe's secrets, we've barely scratched the surface. Entropy, the measure of a system's disorder, might seem like an abstract concept when applied to the cosmos, but it's the hidden heartbeat of the universe's fate. From steam engines to supernova, everything moves toward greater chaos, and dark energy could be the ultimate expression of this relentless march. Picture the universe as a clock slowly winding down. In its youth, packed with the searing heat of the Big Bang, it was a highly ordered system. But as space expanded, that order fragmented, scattering energy into an ever-thinning sea of particles and radiation. Now, with dark energy dominating, the cosmos isn't just expanding, it's accelerating toward a state of maximum entropy, a heat death where no useful energy remains to sustain motion or life. This grim destiny isn't just a consequence of dark energy's push, it might be woven into its very nature. Quantum fluctuations, those fleeting bursts of energy in the vacuum, aren't just random noise. Each one is a tiny increase in the universe's entropy, a microscopic step toward equilibrium. When virtual particles pop into existence, they borrow energy from the vacuum, creating fleeting pockets of order. But when they vanish, they leave behind a trace of chaos, like footprints in cosmic sand. Over unimaginable scales, these flickers could add up, driving the universe toward a state where even the vacuum's energy is too diluted to stir the cosmos. But here's the twist: entropy and quantum fluctuations might be locked in a dance more intricate than we've realized. In black holes, for instance, entropy isn't just a measure of disorder, it's tied to the surface area of the event horizon, a direct link between gravity and quantum mechanics. This holographic principle suggests that the universe's total entropy isn't determined by its volume, but by its boundaries, like information encoded on a cosmic hard drive. If true, dark energy's acceleration could be the universe's way of maximizing this boundary, creating more surface for entropy to spread. It's as if space-time itself is stretching to accommodate the void's growing chaos. The implications are dizzying. If dark energy is entropy's ally, it could explain why the vacuum's energy density stays constant as the universe expands. Unlike matter or radiation, which dilute over time, dark energy's persistence might reflect entropy's insatiable appetite for more room to grow. Some theories even suggest that dark energy isn't a static force, but an emergent property of this cosmic scrambling, a thermodynamic echo of the universe's relentless drive toward disorder. Yet mysteries linger. Why does the vacuum's entropy align so perfectly with the observed strength of dark energy? Is this a cosmic coincidence, or is there a deeper law dictating the balance? The answers might lie in the quantum realm, where fluctuations and entropy share a common origin, or perhaps we're glimpsing a shadow of something grander, a universe where thermodynamics doesn't just describe decay, but actively shapes the fabric of reality. One thing's certain, the heat death isn't just an end, it's a lens, revealing how the universe's smallest quirks and largest structures are bound by the same invisible threads. And as we untangle them, we might find that dark energy isn't just pushing galaxies apart, it's writing the final chapter in thermodynamics' oldest story. String theory dares to ask a question that would make even Einstein pause. What if our universe is just one slice of an infinitely richer cosmic reality? Imagine space isn't the three-dimensional stage we perceive, but a thin membrane, or brain, floating in a higher dimensional expanse, like a sheet of paper suspended in a vast, unseen wind. This isn't just a sci-fi daydream, it's a serious hypothesis that could explain dark energy's mysterious push, tying it to the gravitational tides of those hidden dimensions. At the heart of string theory lies a radical idea. The fundamental particles we know, quarks, electrons, photons, aren't dots at all, but tiny, vibrating strings. Their different harmonies give rise to different forces and particles, much like how a violin string produces distinct notes. But here's the twist: for the math to work, these strings need to vibrate in not just 3 spatial dimensions, but 10 or 11. Where are these extra dimensions? They could be curled up impossibly small, like the tightly wound threads of a carpet's weave, or stretched beyond our perception, accessible only to gravity, and perhaps dark energy. This is where the brain world scenario unfolds. If our universe is a 3-dimensional brain adrift in a higher dimensional bulk, dark energy might be the gravitational influence of neighboring brains, or the bulk itself, gently tugging at our cosmos from beyond the veil. Picture 2 soap bubbles floating close together. Even if they never touch, their mutual gravitational pull could distort their surfaces. Similarly, a nearby brain, or the curvature of the bulk space, might exert a pressure we perceive as dark energy's repulsive force. The math behind this is staggeringly complex, but the payoff could be revolutionary. String theory naturally incorporates gravity into quantum mechanics, offering a potential solution to the vacuum energy catastrophe. In some models, the extra dimensions act like cosmic pressure valves, siphoning off the quantum vacuum's predicted energy into higher dimensional space, leaving only the faint residue we call dark energy. It's as if the universe has been hiding its excess energy in dimensions we can't see, like stashing clutter in a closet to keep the living room tidy. Critics argue string theory remains untested, its elegance overshadowed by a lack of experimental proof, yet supporters point to subtle clues. If higher dimensions exist, they might subtly alter gravity at microscopic distances, and effect labs are hunting with exquisitely sensitive torsion balances. Others speculate that colliders like the Large Hadron Collider could produce exotic particles or miniature black holes, fleeting evidence of these hidden realms. Even without direct proof, the implications are mesmerizing. If string theory is right, dark energy might not be a property of our universe at all, but a cosmic echo, a shadow cast by dimensions we're only beginning to imagine. The acceleration of galaxies, the fate of spacetime, even the nature of reality itself could hinge on this grander architecture, and while the math may live in abstraction for now, the quest to test it is anything but theoretical. From lab experiments to space telescopes, we're inching closer to answers that could rewrite not just dark energy's story, but the very definition of existence. The vacuum of space isn't just empty, it's a quantum symphony, humming with fluctuations so subtle they've eluded detection for decades. But what if we could tune into this cosmic static directly, measuring dark energies whisper with instruments so precise they border on the miraculous? Enter the next frontier, quantum sensors, machines so sensitive they can detect gravitational waves from colliding black holes or the faint magnetic fields of a single neuron. Now scientists are retooling these marvels to hunt for dark energy's fingerprints in the void itself. Atom interferometers sit at the cutting edge of this quest. Imagine clouds of ultra-cold atoms, chilled to near absolute zero, behaving like waves rather than particles. By splitting these atomic waves with lasers and letting them recombine, researchers can measure infinitesimal shifts in their paths, changes that might betray the influence of dark energy's pressure on spacetime. It's like using atoms as quantum seismometers, feeling for tremors in the fabric of reality itself. Recent experiments have already used this technique to measure Earth's gravity with staggering precision. Scaling it up could reveal how dark energy subtly warps local spacetime, a distortion hidden in plain sight. But the real game-changer might lie in quantum optics, where light itself becomes a probe for the vacuum's secrets. Advanced photon detectors, like those used in quantum entanglement experiments, are now being adapted to hunt for anomalies in the Casimir Effect, the same quantum force that pulls metal plates together in a vacuum. By observing how light scatters or shifts in carefully engineered nanocavities, physicists hope to spot deviations from theory that could signal dark energy's influence at microscopic scales. Picture a hall of mirrors where every reflection carries a faint imprint of the void's hidden energy, detectable only by quantum light's exquisite sensitivity. Then there's the wild card, quantum squeezed states. In these bizarre setups, particles are manipulated to reduce uncertainty in one property like position at the expense of another like momentum, effectively squeezing quantum noise out of measurements. Applied to gravitational wave detectors like LIGO or future space-based observatories, this technique could amplify sensitivity to spacetime ripples caused by dark energy's cumulative push across cosmic distances. It's the equivalent of filtering out the roar of an ocean to hear a single drop, except the ocean is the universe's background hum, and the drop is dark energy's nudge on passing gravitational waves. The challenge isn't just technical, it's philosophical. Quantum sensors force us to confront a strange truth. To measure the void, we must embrace uncertainty. Heisenberg's famous principle dictates that the very act of observation disturbs the system being studied. So how do you measure something as elusive as dark energy without altering its behavior? The answer might lie in quantum non-demolition measurements, clever protocols that extract information while minimizing back reaction. Think of it as weighing a feather without touching it, using quantum tricks to infer its mass from the air currents it disrupts. What makes this pursuit so electrifying isn't just the potential discovery, it's the sheer audacity of the tools. We're no longer limited by the clumsiness of classical physics. Quantum sensors operate in a realm where reality itself flickers between states, offering glimpses of laws we've only guessed at. And if they succeed, the payoff could be monumental, not just confirmation of dark energy's quantum roots, but a roadmap to harnessing the vacuum's energy itself. After all, the same fluctuations that might drive cosmic acceleration could, in theory, be tapped as a boundless energy source if we learn to speak their language. Of course, skeptics abound. The signals these sensors chase are unimaginably faint, buried under noise from cosmic rays, thermal vibrations, even quantum jitter. Distinguishing dark energy's whisper from the universe's background chatter will require not just better instruments, but new statistical frameworks to separate signal from illusion. Yet history shows that every leap in precision has unveiled deeper layers of reality, from the discovery of the atomic nucleus to the detection of gravitational waves. The quantum measurement revolution isn't just about sharper tools, it's about rewriting what we thought was possible to know. As these technologies mature, they're blurring the line between particle physics and cosmology. A lab bench experiment with chilled atoms might one day reveal why galaxies fly apart, linking the infinitesimal to the infinite, and in that connection lies the true promise that dark energy isn't an abstract cosmic force, but a phenomenon as tangible as the quantum sensors straining to detect it, a mystery not beyond our grasp, but just beyond our current reach. The void may be silent, but it's not mute. We're finally building the ears to hear its song. If the universe truly hums with quantum fluctuations and dark energy's unseen push, then our existence isn't just accidental, it's statistically miraculous. Picture this: every thought, every galaxy, every fleeting moment of life arises from the same restless void that birthed the cosmos. We're not just observers of the quantum dance, we're part of it, temporary patterns in an infinite cosmic tapestry where even emptiness crackles with potential. This realization doesn't just reshape physics, it redefines what it means to be. Consider the odds. For conscious life to emerge, the universe had to balance its constants with absurd precision. Dark energy's strength, the quantum vacuum's energy density, even the stability of atoms, they all teeter on a knife's edge. Tweak any one value slightly, and stars wouldn't ignite, molecules wouldn't form, and we wouldn't be here to ponder it. Some physicists argue this fine-tuning points to a multiverse, where countless universes bubble into existence with random laws, and we simply inhabit the one where the numbers lined up right. Others see it as evidence of something deeper, a fundamental principle that entwines consciousness with the fabric of reality itself. But here's the twist: if we're born from quantum chaos, does that make us insignificant or unimaginably rare? On one hand, we're fleeting ripples in a vast quantum sea, here for a cosmic blink before dissolving back into the void. On the other, the fact that the universe evolved creatures capable of unraveling its mysteries suggests something profound. The cosmos isn't just a cold, indifferent machine, it's a system complex enough to reflect upon itself. In that sense, we're not just accidents, we're the universe's way of understanding its own existence. This duality forces us to confront questions that straddle science and philosophy. If dark energy's push is tied to quantum fluctuations, does that mean free will is just an illusion, our choices predetermined by particle interactions too small to see? Or does the inherent randomness of the quantum realm grant genuine unpredictability, a cosmic wiggle room where consciousness can steer its own path? The debate isn't academic. It cuts to the heart of whether we're passive passengers or active participants in a universe that's still writing its own rules. Then there's the existential curveball. If the vacuum's energy can spawn particles from nothing, could entire universes bubble into existence the same way? Some theories suggest our cosmos might be one of many, a single quantum fluctuation in an endless foam of realities. In that scenario, dark energy isn't just a local anomaly, it's a signature of a far vaster multiverse, each with its own laws and histories. The implications are dizzying. If true, we're not just stardust, we're statistical inevitabilities in an infinite ensemble of possibilities. Yet for all the grand theories, one truth remains humbling. The more we learn about dark energy and the quantum vacuum, the clearer it becomes that reality is far stranger than we ever imagined. The ground beneath our feet, the air we breathe, even the neurons firing these thoughts, all of it is underpinned by forces that defy intuition. We're left staring into a cosmic mirror, wondering if the reflection staring back is solid or spectral, permanent or fleeting. The answers might lie not just in equations, but in the very act of asking. Because in a universe where emptiness brims with energy and particles blink in and out of existence, the line between science and philosophy isn't just blurred, it might not exist at all. From the quantum foam's restless churn to the cosmic void's silent push, the dance between dark energy and vacuum fluctuations isn't just a scientific puzzle, it's a revelation. Every layer we peel back exposes a universe that defies intuition, where emptiness crackles with energy, and the fate of galaxies hinges on the smallest flickers of quantum uncertainty. We've traced these threads from lab experiments with metal plates whispering in vacuum chambers to telescopes capturing light from dying stars billions of years away. Yet for every answer, a dozen new questions emerge. Why does the vacuum's math diverge so wildly from reality? Could dark energy be a shadow of higher dimensions, or the echo of a symmetry long broken? The beauty of this mystery lies in its universality. It touches everything from the infinitesimal, where particles blink in and out of existence, to the infinite, where entire galaxy clusters flee into darkness. Even time itself might be entangled with the void's energy, its arrow guided by the same quantum chaos that fuels cosmic expansion. And while theories abound from holographic principles to phantom energies, apocalyptic rip, each is a stepping stone, not an endpoint. The greatest lesson isn't in the answers we've found, but in the humility they inspire. The cosmos operates on scales and timelines that dwarf human experience, yet here we are, atoms forged in stars, deciphering the universe's coded whispers. What comes next? The horizon gleams with promise. Euclid's galaxy maps, quantum sensors probing spacetime's fabric, even tabletop experiments hunting for hidden forces. Each could be the key that unlocks the next revolution. Perhaps dark energy will remain enigmatic, a cosmic joke about the limits of human knowledge, or perhaps in unraveling it, we'll stumble upon a truth so profound it redefines reality itself. One thing's certain, the journey isn't solitary. Every comment, question, and shared insight adds to the collective search. So tell us, what cosmic connection left you awestruck? And if you're hungry for more deep dives into the universe's grandest mysteries, hit subscribe. The cosmos has countless stories left to tell, and we're just getting